Hello my dear students, welcome back. So in the previous classes like your 10th standard we studied about this, that's a force on a current carrying conductor in a magnetic field. You all know that this concepts which you have forgotten, I want to recap that. Okay, here we have a copper wire, the current is flowing through that. When I pour the iron filings, you can see the arrangements of the magnetic field, correct? So some force is exerted on this current conductor. This was experiment done by the Mary Ampere. Here, when you consider this wire, current carrying wire, and there is some force exerted on this, how we can identify? So he started doing one experiment. He will do the experiment by taking this small rod, think it's 5 centimeter. I will take this rod and I will do this kind of arrangements. Okay, experimental setup. B will be tied like this at A. Then I'll bring a horseshoe magnet north and south, where south should be upwards, okay, and north should be downwards. Okay, fine. Now I will take the wire and I want to close this circuit. Okay, I'll just connect everything. I took a battery and a key. Now the current is passing through this particular conductor. What it happens when the current passes through the conductor? So the conductor will be attracted towards the north. Some force is exerted on that conductor, so it is attracted to the north. Now you have seen it attracted to south. How? I reverse the direction of the current. When I reverse the direction of the current, the force also will be changed. The direction of the force is also reversed when the direction of the current to the conductor is reversed. Now what I will do, I will reverse the magnetic field. Okay, north will go south. See again how the attraction is taken place. The direction of the force on the conductor depends on the direction of the current. Okay, so current is up. Okay, magnetic field is like this, both are 90 degree, so the force will be mutually perpendicular. This was explained by Fleming's left hand rule. Forefinger indicates magnetic field, middle finger indicates the current, and thumb finger indicates the force acting on the conductor. All three should be mutually perpendicular to each other. Okay, so this is called as Fleming's left hand rule. This is for the positive charged particles. Usually we'll consider the force acting on the conductor to the positive charged particles. So this about the magnetic field, whatever you have studied in your 10th standard, or how the force is exerted on this current carrying conductor. Okay, now we will come back for the applications wherever we are using this Fleming's left hand rule. Electric generator, motors, loudspeakers, speakers, mic, and this measurements, everywhere we are using. Now we study whatever it is there in your second PUC. Force on a current carrying conductor which is placed in a magnetic field. I will place a conductor in the presence of the magnetic field. So first let me write the magnetic field. Okay, so here B representing a magnetic field direction is like this. So this is what my magnetic field. In the presence of the magnetic field, I will place the conductor. Which conductor? It's a current carrying conductor. Okay, here in the conductor you will be having electrons, positively charged particles also, negatively charged particles also. Electrons will be moving. Okay, as the thing, it's very clear that the force on a current carrying conductor. So whatever the conductor you are considering, there will be a current carrying conductor. Okay. Magnetic Lorentz force, which you have studied, when the charge is moving with some velocity in the presence of magnetic field, there will be a magnetic Lorentz force. Is it or not? So if Q, charge is moving in the presence of magnetic field with some velocity, therefore how I got the relation? F is equals to QVB. So V cross B V2. So if you are not getting, please go back to the previous videos, right? I did in the volume 3, volume 4 itself. Like that, I will calculate the complete force which is acting on this particular conductor. The Lorentz force, I will sum up. By that, I can identify the force. Now here we are considering an electron, where electrons will be there in the conductor. your current direction in this way, you always remember that electron direction is always opposite direction of your current, because usually we consider current is a movement of the positive charge, electron is a movement of the negative charge. Both will be moving in an opposite direction. Okay, so the current is moving in this particular direction. I am seeing in the if you see, you can observe, and the electrons is opposite, it is moving opposite to it, both are opposite to each other. Okay, now the electron will be moving with some velocity. Here which velocity I should consider? Drift velocity, because as the current supplied, the electron will start drifting, therefore the electrons is having a velocity Vd. You know that the charge is moving in the presence of magnetic field, there will be exerting some force. Okay, so magnetic field is over here, Vd velocity. So we have magnetic field and the charge is moving with the velocity, so I can consider the magnetic Lorentz force. I taught you this. Even by using the Fleming's left hand rule we can do it, but in Fleming's left hand rule we are considering for positively charged particles. Okay, but I took here electron. Usually Fleming's left hand rule is for positive charged particles, but here we have an electron. Okay, fine. First we will understand how to apply the Fleming's left hand rule over here in the presence of magnetic field and this velocity. The electron is negative. Now I will consider the direction of the positive charged particle, or I can say current. Current direction is nothing but what? Current direction is nothing but positive charge direction. Okay, in this way, right side, I'll consider the direction of positive charge particles. Let me take it as a I, and for your reference, you can take it as a plus sign. See, you can use whatever I thought before, V direction, B direction means your F will be outward as usual, which I have taught you in the previous class. Now I am taking for the Fleming's left hand rule. See here, left hand rule, where your forefinger represents the direction of the magnetic field. Okay, forefinger represents the direction of the magnetic field and the central finger represents the direction of the current. Okay, or I can say a moving charged particles with the velocity v. Okay, this is forefinger represents the B and the center finger represents the direction of velocity. Next, the thumb indicates the direction of the force, or even I can say it's a Lorentz force. Okay, this thumb indicates the direction of force. Okay, now we have magnetic field, we have current, that is nothing but a moment of the positive charge Vd. Okay, so what will be the direction of your force? Force will be outward direction, is it or not? This is what the I, and B is nothing but a forefinger. This is center finger and this is forefinger. Where will be your thumb finger? It will be outward. Okay, you can do in your mobile screen itself. Okay, your force will be outward. Ma'am, suppose if there is an electron, how to consider if there is a no current passing through that? You can use a right hand rule, Fleming's right hand rule. It doesn't make much difference. Okay, but standard is always, you should remember, left hand rule only. Okay, standard is always left hand rule itself. So if it is for an electron, let me take a right hand rule, go through here. See, Vd for electron, negative particles, you are taking right hand. Okay, for if it is negative, it is you are taking right hand, and for left hand it's for positive. Okay dears, see, center finger Vd and thumb finger B, again outwards you will get the force. Okay, standard is always left hand itself. Fleming's left hand will consider for positive, Fleming's right hand rule will consider for negative particles. So here we will consider a derivation. It's a very important for your examinations too. The force acting on the current carrying conductor when I placed in a magnetic field. So if the charge is moving with some velocity in the presence of the magnetic field, So I can say that there is some force is exerted, correct? So how to write in the expressions, how to make a proper equation for that, correct? No, because we have the force and velocity, magnetic field. Which formula we are going to use? You all know that we are going to use F is equals to QVB, where V cross B, because all three are perpendicular. Okay, fine. Now the magnetic Lorentz force, okay, magnetic Lorentz force is equals to, here charge particle means I need to consider which particle. Here we have an electron, okay. So magnetic force or magnetic Lorentz force is equals to, in the place of charge I am writing minus E, okay, V cross B, okay, your V cross B, Q into V cross B I will write. In the place of Q I am writing minus E, in the place of Q I am writing minus E. Is that clear? Okay. So let us write the next equation like this, or this drift velocity, I can say it as a V is a drift velocity, okay. Now let me write down this negative sign, minus E represents what? It's a negative charge particle, that's it. So no need to confuse, okay. Here whatever the V we are calculating for electron, or force we are calculating for the electron, it's not for one particle. We want for all the particles which are present in the conductor. So I am taking number of free electrons per unit volume. This I taught you many times for almost 4 derivations, okay. We are taking n, where with respect to volume, therefore what I need to consider, number of free electrons per unit volume, where volume I can write area into length, correct. Here this is an area, okay, that is a cross sectional area, and this is what your length, let me take it as L, okay. So I can write it as a volume is equals to cross sectional area into L, okay. So this I can write it as what? NaL, correct. Number of free electrons per unit volume, N. So I will take it as what? NaL. Okay, fine. So let me write down that we are not considering the force for only one electron, so we are considering the force for all the electrons. Therefore I can write it as total number of electrons is equals to NaL, okay. So it's not for one electron. What I should write here? So this will be equals to for all the electrons which is present there, the force acting on all the electrons, okay. Therefore the total force F with the vector quantity will be equals to NaLe, that is nothing but a minus E bracket V cross B. So remember this V is what? It's a drift velocity. If you want, you can write D here, okay. So this is about the total force which is acting. Now I will try to simplify. This will be equals to N, okay, NaL into minus E, it's a minus NaLe Vd cross B, because the electrons is drifted opposite to the current electric current, therefore I am taking Vd, okay. This Vd cross B, I will now multiply it with this, that is minus NaLe into Vd cross B. So when I multiply it, so I will be getting minus NaLe, okay, Vd with the vector form cross B. Now we will take this, okay, this in the another form. You have seen that derivation somewhere, where it's in nothing but current electricity, correct? That I will rearrange that, where I is equals to NAVD, correct? NAEVD, which we have known from the current electricity concept. So please recap that, you will understand. So NAEVD, it's a value for your current, correct? No, here negative sign indicates what? Just a direction. The electron is going opposite direction of the current, that's all. So here when I am considering scalar of the current, no need to write. If I am considering the vector of the current, I need to write the negative sign, okay? If I am writing in the magnitude, no need to write that negative sign. So that negative, it's indicating the opposite of the current, so no need to worry about that negative sign. So if you are writing the scalar quantity of the current, negative sign will not impact on that, okay? Now what I will do, I will multiply by L both the side, therefore it becomes this becomes IL is equals to NALEVD. You can observe same thing you have here with a negative sign. Negative indicates a direction. So in the place of that, I can write it as IL. Is it or not? In the place of NALEVD, I can write it as what? I can write it as NALVD. Now in a vector notation, how to write in the vector form? Because the vector form is important. VD is a vector, B is a vector. Therefore, IL I need to write in the vector form. How to write in the vector form? Here current we have with respect to length. Ma'am, you said current is a scalar quantity. No, current I am taking with respect to length. Therefore, it is a vector quantity. Okay. IL is a vector. NALEVD. Okay. So here I am writing with the vector notation because I am considering the direction of the current. Moving charge particles velocity I am considering. Therefore, I require this value, that is a vector value, okay? That is a VD. Here also VD. Everything is now matched. In the place of NALEVD, I can write it as IL vector, okay? This I am going to represent, that is minus NALE. Why I am writing minus? Here I am not writing minus because it is a scalar over here. Here it is a vector. Okay, including the direction I am considering. IL. Okay. So minus NALEVD, in the place of that I can write it as IL vector. Okay. Now let us write in this particular place, that is what? Minus NALEVD, that I will write it as IL above vector. Okay, write down. So that is equals to F vector is equals to, that complete it becomes IL vector cross B. Okay, this is what an expression for the force which is acting on that particular conductor in the presence of a magnetic field. Now when I am considering a conductor, so the current is passing through this particular conductor I, okay, and this is what it is having the length, and your magnetic field is something making an angle. Okay, this is what your magnetic field, and it is making an angle with that conductor, that is nothing but theta. Okay, theta. Now here we have a cross product, so in that cross product I can write it as what? Sin theta. So F is equals to ILB sin theta, correct? B we have, B is making an angle theta, therefore I can write it as what? Here it is making with the which? IL, you need to write it as IL. IL is a complete vector quantity, not only L, it is a IL. Okay, so the angle made between IL and B, that is nothing but theta. Okay, therefore your force will becomes ILB sine theta. The cross product will becomes ILB, okay, sine theta. Thank you all. Have a nice day. Okay.